Let's now define two important quantities we need to make sense of our power spectrum. The first is the frequency resolution, df, which we define as 1 over big T, or in words, the reciprocal of the total recording duration. The second quantity we must define is the Nyquist frequency, which we'll call f sub nq, which is equal to the sampling frequency over 2, or 1 over 2 times the sampling interval. In words, the Nyquist frequency is half of the sampling frequency. Where remember, f naught, our sampling frequency, is 1 over delta. For the clinical EEG data considered here, the total recording duration is 2 seconds. Remember, big T is equal to 2. So the frequency resolution, df, is 1 over 2 seconds, which is equal to 0.5 hertz. The sampling frequency, f naught, is 1,000 hertz for these data. So the Nyquist frequency is half of 1,000, or 500 hertz. There's much more to say about both quantities with intuition to be gained, as we'll see in the next lectures. For now, let's simply use both quantities to consider how MATLAB relates the indices and frequencies of our vector, SXX. Here's a visual representation of this relationship. Notice that for the first half of our variable SXX, the frequency axis increases in steps of the frequency resolution, df, which in this case is 0.5 hertz, until reaching the Nyquist frequency, FNQ, which here is 500 hertz. The maximal frequency occurs just past the halfway point of the indices. At index, let's call it little j, is equal to n over 2 plus 1. Beyond this index, the frequency axis is negative. Here, the magnitude of the frequency becomes smaller and smaller until the value negative df is reached, at index little j equals big N. We may now utilize a useful property of the Fourier transform. When a signal is real, in other words, the signal has zero imaginary components, the negative frequencies in the spectrum are redundant. So the power we observe at frequency f naught is identical to the power we observe at frequency negative f naught. For this reason, we can safely ignore the negative frequencies. These frequencies provide us with no additional information. Because the EEG data are real, we conclude that the negative frequencies in the variable SXX are redundant, and we can ignore them. We therefore need only plot the variable SXX for the positive frequencies, more specifically, for index 1 all the way up to index n over 2 plus 1. This conclusion matches our visual inspection of the variable SXX.